Greetings, everybody. Here's a question from our assignment on MyMathLab that I think would be good to show you. I'll let you read this, and I'll start with my summary down here, and I'll go from there. Okay, so we have this situation where there's a boat some distance away from a dock. There's a point on the dock 4 feet above the water where a rope is attached and reels in the boat. Okay, as the boat is reeled in, then by the rope, then the boat also moves along the water. And it would seem pretty obvious that the speed the boat moves on the water is going to be different than however fast the rope is reeled in. Okay, so there's our situation. And additionally, I know that the rope is reeled in at 5 feet per second. All right. Okay, and that's all I've got for the most part. And I want to solve for this. If the rope is being reeled in at 5 feet per second, how fast is the boat moving on the water? I think it's obvious that the speeds will be different, but can you, with one, find the other? All right, that's the issue. Now, more specifically, we're being asked if you know how fast you're reeling in the rope. If you're reeling in the rope, 5 feet of rope for every second that goes by, then how fast is the boat moving on the water when it's 13 feet away from the base of the dock? Okay, so that's the full statement of the question. Now, when I read this and it says that the rope is being reeled in 5 feet of rope for every second that goes by, then I interpret that as the derivative dz over dt is negative 5 feet per second. So why negative 5? Well, as this question was described, we have to impose some geometry on it. And we see, well, the boat and the capstan and this point right beneath the capstan in the water, the capstan reels in the rope. They make a right triangle. Okay, so we'll use that geometric construct to solve this. And if that's the way that we're doing it, and I call z the hypotenuse, I have to say that dz over dt is negative. The rope might be being reeled in at 5 feet of rope for every second, but as I have to attach variables to this and a geometry to it, then z, the hypotenuse of this triangle, which represents the length of rope, is getting smaller by 5 feet for every second that goes by. So I need to say that that's negative. Okay. All right. Now, there's my full setup. I don't think I need to say anything else about it. Let's do like this. All right. So let's go over the procedure real quick. I try to be consistent when I do this, use the same procedure every time, even though you could vary what I do a little bit and it's fine. All right. I'm still going to try to do things consistently. So we need to start with a true equation that relates to variables that we're working with. Okay. So if I know how z is changing and I want to know how x is changing, I need some equation that relates the x and the z. And as I look at this, I see that I have a right triangle and x and z are sides of that triangle. So I could use the Pythagorean theorem. A true equation about this triangle is that x squared plus 4 squared is z squared. That's true. So we'll start there. Okay. The next step, take the derivative with respect to time using applicable rules for that equation. So as I do that, the derivative of x squared is 2x, but then times dx over dt. And we follow it to dx over dt because of the chain rule. X is ultimately a function of time. That's why we say the derivative is not just 2x, but it's 2x times dx over dt. The derivative is 16. Well, 16 is a constant. It's not changing. The derivative would tell me how something is changing, and 16 is always 16. It's never going to change. And the derivative of z squared is not 2z. It's not just 2z. The derivative of z squared is 2z times dz over dt. Okay, why? Well, because z is a function of time. All right, so there is that part. I took the derivative with respect to time. Here, I use the rules as applicable. The third step, I need to solve for whatever derivative I'm looking for, but I need to make sure at this stage to incorporate all the known information that I have. So think about it like this. I want to know what dx over dt is. And it shows up in my work here in the second step. But unless I can tell you all these other things, there's no way to definitively solve for this in this equation. You know, I would have to know what x is, I would have to know what z is, and I would have to know what dz over dt is. I would have to know all those things in order to find dx over dt out of my work here. But I can do that. For example, I interpreted from the beginning that dz over dt is -5, so I can put that in. Then I was told that x is 13, so I can put that in. What about z? Well, I'll have to figure z out. Let's see, so if I know x is 13, and I know this side was 4 to begin with, then I can find z by the Pythagorean theorem, and it's square root of 185 feet. So then I can find z. So see, I either already have or I can find everything in this equation, all right, except dx over dt so far. So now, because I know everything in this equation, I either already knew it or I figured it out, and dx over dt is the only thing left, I can solve for it. I could, you know, divide 2 times 13 on that side over there. All right, and if I do that and I do a little canceling with the 2's, I'll get this, -5 root 185 over 13. With a little rounding, that's -5.23 feet per second. Okay, so there's your dx over dt. Now, why isn't -5.23 feet per second the answer? I see here on my math lab, it says 5.23 feet per second. Well, think about the question. So, it's basically saying, how fast is the boat moving on the water? What I've figured out is that this aspect of this triangle, this horizontal aspect, the base of the triangle, this side that I'm labeling x, what I figured out is that that side of the triangle is getting smaller by 5.23 feet for every second that goes by. Now, I can interpret that as the speed of the boat on the water, but I got to lose the negative. You know, the boat, the base of that triangle might be getting smaller by 5.23 feet per every second, but the boat moving on the water through space, it's just moving 5.23 feet per second. So that's why the answer is positive, whereas from my work, I get a negative number. But I know better. I know I can interpret it correctly from there. Now, as a bonus, I want to explore this a little bit more in this way. So I've already answered the question on my math lab, and if you're happy with that, that's fine. But I'm curious for you to think a little bit about this. Does dx over dt, which we can interpret as the speed of the boat on the water, does it depend on the position of the boat? Like, you know, if the boat were further away or closer, would we get a different number for dx over dt? So that's my first question. And my second question is, what would you expect dx over dt to be if the boat was really far away? So I think there's this limiting aspect of the problem here. As the boat gets further away, dx over dt does something in particular. Okay, so just think about that for a second. So answer to the first question is, yeah, how fast the boat moves, even though the rope is being reeled in at a constant rate. So say, no matter how far up the boat is, no matter where the boat is in space, the rope is being reeled in 5 feet per second. But even though the speed the rope is being reeled in is not changing, then you can see that, yeah, as the boat was further or closer, it's going to be moving a different speed. It doesn't matter that the speed the rope's being reeled in is the same all the time. Because think about it. If x is a different number, we're going to get a different number for z. It's going to change all this, and we're going to get a different speed. So yeah, dx dt will totally depend on the position of the boat. As far as what I would expect it to be if the boat was really far, think of it like this. This is not the scale, but it's exaggerated. The further away the boat is, the more parallel x and z are. And so here's my own instinct, maybe yours too. The more parallel these are, the more their speeds are going to match each other. They have to. If you want to see that, let's say that the boat was 500 feet away. If you could imagine it being tethered by a rope and reeled in at 500 feet away. I could solve for z. I could take this right here, solve it for dx over dt, and put in the numbers I've got. Okay. You know, I know that z is now root 250,016 and x is 500. Still, I'm just working out of this equation, putting my numbers in. And look what I get, negative 5.0002 feet per second. So yeah, that boat's far out there. It's going to be basically matching the speed of the rope being reeled in. Okay. So, and I think this number bears it out. Now, you could prove this if you wanted to. Dx over dt will approach. Remember when we learned limits early in the course? Well, here's a limit. Dx over dt, the speed of the boat on the water, will approach dz over dt, the speed the rope's being reeled in, as x goes to infinity, as the distance of the boat goes to infinity. The further it gets out, the more parallel these are, and the more the speed of the boat on the water is going to match the speed that the rope is being reeled in.